So as you do this, you're going higher in energy. So as we can see on the energy curve here, we're at some relative free energy and we're going uphill because as you ionize, that's higher energy. Now what you're forming is a carbocation, so you're sp2 hybridized. And then your nucleophile can attack from either lobe. So this is an intermediate. So from the transition state, you're going into this well. And basically, once the nucleophile attacks from either side, you're going over another transition state where you have partial bond formation and then down to your products. This is only one reaction coordinate diagram that's showing delta G naught, so the free energy change for the reaction is being negative. So keep in mind, these can be positive. I just haven't shown that that specific one on this slide. And again, that's sort of covered in chapter 6. So if you look at the two products you can form, I call this one retention just because the nucleophile is sort of on the same side where the leaving group was. Inversion, it's going to the other side, and you're forming a one-to-one mixture of these. So whatever you start with is overall racemized. So the solvents for SN1 are polar protic, and these can be formic acid, methanol, ethanol, acetic acid. So things that have protic, like OH, is typically, whether it's an acid or an alcohol. The leaving groups are the same as SN2. You're following first order kinetics. So again, that's what the 1 in SN1 means, is that this rate limiting step, so the rate limiting is typically the highest energy step in the diagram, because you have to get over that hump for the reaction to proceed. And it's dependent upon the ionization event. And so what we'll talk about today is stereochemistry and rearrangements. So let's get into the substituent effects, what I talked about, carbocation stability. So we'll call this SN1 rate. So the tertiary substrates are approximate to allylic, benzylic, and neopentyl. So again, the thing you have to recognize about these is that these can be primary, and so we want to understand why these primary ones are sort of on the same rate as the tertiary. So this order has basically, we can explain this using two concepts. First, let me just back up here. I was going to write resonance, but let me talk about induction first. And we'll talk about resonance as well. So resonance will explain these, but let's go ahead and talk about just a straight up tertiary substrate that forms a tertiary carbocation. Why is that the most stable? So say we're dealing with this species here, tert butyl chloride, or the IUPAC name, 2-chloro-2-methylpropane. So in the ionization event, we're showing that bond heterolytically cleaving. Again, that's what this double-headed arrow means. So that's what I mean by double-headed arrow. It's 2 electrons moving. So we end up with a tertiary carbocation. And and then the chloride anion. So notice again, we start neutral. There's no excess of any charge. We're ending up neutral because plus balance is minus, but even though these are ions, they're balanced, right? So that's something we want to make sure we're aware of as we write mechanisms. So why is tertiary stable? So we're going to explain this through the induction effect. So maybe what I can do, that's like a flat drawing. So maybe I'll show it sort of with some perspective. So carbon, put in the p orbital. So keep in mind that's where the plus charge is residing in the p orbital. That's what we mean there. That's where the plus charge is. It's in that p orbital. This last methyl group, I'm going to draw a certain way, and hopefully you'll believe me. So carbon, then I'm going to draw this hydrogen sort of in the plane of that p orbital. This H coming out, and then this H going back. So the reason why tertiary is greater than secondary is sort of explained in the following way. So we know that for an sp2 hybridized carbon, the geometry of these groups bearing the sp2 hybrid orbitals, that's trigonal planar, right? So these are all in a plane, and it's sort of orthogonal to the sheet or the whiteboard that we're looking at. If this p orbital is in the plane, it's electron deficient, right? So that's why we go up in energy to the transition state, then into the intermediate. So carbon that's electron deficient is not happy. If we were to use like anthropomorphism, which is like description, giving emotion to like animals and stuff, like the dog's happy or sad. So we'll say carbon's not happy. How does it become happier? So if we look at this methyl group, we have this CH bond which has 2 electrons in it, right? So, and I'll sort of draw this with the marker. The bond density can sort of go into that electron deficient p orbital, and it makes the carbon happier. So if you imagine each of these methyl groups is sort of doing that, I've only shown it for this one, it sort of makes this more stable. And what we mean by more stable, remember you're going up in energy. So the tertiary, you don't have to go as high. The secondary, you go higher, and primary, you go higher than that. So maybe let me draw that out just so that we can all visualize that. So if you were comparing, your free energy and then time, so here's your starting material. So this would be tertiary. Secondary. And then primary. So that's what we mean about stability. So even though you're going up in energy, the tertiary is the lowest of all of them. So that's what we mean, because it has this stabilization due to induction. So what about resonance? How can we explain that in relation to basically allylic and benzylic? So why if these were primary, why would these be really stable? Let's consider the allylic cation. So say you had this compound. We know that the leaving group is going to be bromide because that's the polarized bond. So when we ionize, we're cleaving that bond. The arrowhead's pointing to the bromine because it has the delta minus. So, yeah, I'll do this for now. And then we know that we can show a resonance form of that allyl cation. So here's a resonance form. So notice the arrow movement. Again, I'm harping on these arrows. The arrow starts where there's electron density, and it's pointing towards something that can accept those electrons. So this double-headed arrow means the movement of those two electrons. As you see here, now it's in a pi bond. Those are migrating over. The terminal carbons are electron deficient. So this is a primary substrate, but it can undergo SN1 because it's stabilized through this arrow here means resonance. So what is the explanation of this? If this is a primary carbocation and we said that's bad, why is it stabilized? So what I'm going to do here, I'm going to use some big arrows or big bonds here. Show these hydrogens. Show this hydrogen going back, forward. So the reason I want to show all these hydrogens is because I'm going to put the orbitals in, and we'll actually talk about them. So we said the carbocation resides in the p orbital. There it is. A pi bond is made of two overlapping p orbitals. And so those have, those are the p orbitals for the pi bond. They have, overlapping electron density in the pi cloud above and beyond sort of the carbon backbone. So what is happening in the resonance structure? The two electrons are migrating over. So I'll sort of show that. And then the plus charge, like I said, ends up at the terminal carbon. So that's how you can stabilize the positive charge, is because you're delocalizing it over the terminal carbons. Are we? Is that a sufficient explanation for categorizing SN1 substrates? Take that as an affirmative. So what I want to do now is talk about a feature of carbocations. So this sort of gets to what Blakely and Aiden have in the chat, and it's related to rearrangement. So this is specific to the SN1 and later on in Module 5 E1 mechanisms. So when you're categorizing your starting material, tertiary, secondary, primary, a phenomenon that can happen is when you compare the reactivity trend. If you're forming like a secondary carbocation, it can actually rearrange to something more stable. So the reason that is, This happens in nature, is because you're going down in energy. So we'll get to something that resembles a neopentyl case in this example. So let me just get to it so you can visualize. So again, in learning this subject, I'm going to present you with a reaction, and we probably haven't talked about the specific transformation yet, but knowing what you know about observing and describing things, this example will help you learn. So don't get frustrated that we haven't formally talked about this, because I'm going to ask you questions and we'll work our way through it. And really asking questions is probably the best thing you can do to help yourself learn this material. So here's the reaction. You can consider those are the facts, and you're presenting them, and now we want to explain how do we get there. So consider it like you're in a forest and you need to get from point A to B, but right now it's not exactly clear. So we're asking ourselves questions about the path. And the path is describing that reaction coordinate. How are we going to go along this to get from the starting material to the product? So some questions I'll ask you. These may seem obvious, but I think if we're all on the same page, then we can really understand how this is done in terms of writing a mechanism. So what is the name of the starting material? So 3-methyl-2-pentanol. So everyone, so I sort of wrote in red as the IUPAC nomenclature for the carbon backbone. So maybe let me do the same for the product. So Aiden says 3-methoxy, 3-methylpentane. So I'll buy that. Let's just use that because it sort of gets us moving here. So let me ask you a question. Looking at the starting material and looking at the product, is there something that seems quote unquote weird to you? And if there's something that's weird, can you write in the chat or unmute? What's strange about what's happening? So Aiden says the leaving group and the nucleophile are on different carbons. So that is the correct observation. That is sort of quote unquote what is weird. And so that is a fact, right? So we're accepting that as fact. So now we have to write a mechanism that accounts for that fact. And, you know, in all the times I've taught this class, I think this is sort of the logic that students have trouble following, because you really need to let the facts guide you. You have to propose something that's logical in terms of pushing an arrow, obeying pKa, obeying Lewis structures. Take it nice and slow, and you will end up at the correct mechanism no matter what. So, looking at the conditions, how would you describe how would you characterize the starting alcohol? What would you classify the alcohol as? So we have secondary. So the product is, the main functional group is an ether. So how would you classify sort of the carbon bearing the oxygen in the product? So yeah, we're going to say tertiary. So that's the key here, right? You're starting with something secondary and you're ending up with something tertiary. And I'm referring to sort of the CO bond. So we have an alcohol in acid. What is the first thing we should do in showing a mechanism? So we can say tertiary ether. That's perfectly fine. I think we'll all understand that. So in terms of showing an arrow, what's the first thing we should do if we're starting with an alcohol, we're in the presence of acid, and then we have methanol as solvent? What would you do if I could no longer have rational thought and your thoughts controlled my arm? How would my arm move? So I'm going to give you a clue here. Can I rephrase the question, Alex Trebek? So here's the quote unquote clue. I'm going to use blue to spice it up a little bit. If this is an acid, this is your solvent. If hydronium is the acid, what is the alcohol? What's the reactivity of the alcohol in this reaction to start with? Would the hydronium ion attack the oxygen of the alcohol? So I wouldn't really phrase it that way, because we want to use the phraseology to help us write the arrow. So if the hydronium's the acid, the alcohol must be the what? So it has to be the base. So let me just start writing this sort of down here just to clear things up a smidge. So a base abstracts a hydrogen, right? So we have the hydronium. We're protonating. So we have an acid-base reaction. So I'm showing equilibrium arrows. So that means the equilibrium is happening very fast. It's a proton transfer. PT, proton transfer. Notice the migration of the plus charge here to there. The conjugate base is water. So you're forming water. I'm not going to draw that because it's not, well, maybe I will. Just to show you how the proton transfers occur. So now we're here, right? What is the next thing I should do? I don't know what you mean by get a C. So keep in mind, we've moved. We're in the forest. We've moved a little bit forward. We're here. Our ultimate goal is to get to this thing. How can we transform this one more step that sort of gets us here? Keeping in mind we're SN1 mechanism at this point. So we are going to break this bond, right? We're going to ionize it. And how do you know that has to happen? Because your eyeballs look here. See this carbon 2? It has HOH. Now see it here. It has HH. You know you have to break that bond because we have to get to that. So again, we're ionizing. So at this point, this is the slow step. So how do you classify this carbocation? So yeah, it's secondary because we started with a secondary alcohol. So when it ionizes, this is secondary. So once you form, and this holds for any mechanism you're doing, once you form a carbocation, you are now at a decision point. And so this is why I strongly encourage you as students to write this stuff down and not do it in your head, because you're coming to these decision points where you have to evaluate the structure when you ask these questions. This is a secondary carbocation. You ask, can this rearrange to become something more stable according to this stability trend for carbocations? You're sitting at secondary. Can it rearrange to form something that's tertiary? And this is the logic you use to do that. So I'm gonna call the carbocation, I'm gonna call it the alpha carbon. So using the Greek alphabet, I'm going to call the carbons next door beta carbons. I'm going to call this beta, and then the next one over here beta prime. And I'm saying it's beta prime because this is a methyl. It's CH3. This is tertiary. It has a methine. So this has 3 hydrogens. This has 1. So in this case, Beta prime is more substituted than beta. So why is that important? So let me draw this hydrogen in. So we haven't been drawing that hydrogen, but I put it in there now. So what can happen is after you evaluate all the beta carbons, if you can migrate a hydrogen or a methyl group to the carbocation and form something more stable, that will happen. So there's that hydrogen. If I show that hydrogen moving over now as hydride, so those two electrons in that CH bond, so it's called hydride because it's like H minus moving over. So I'm sort of using that same nomenclature that I did for the prior one, just to show you, keep things consistent for now. So here's your alpha carbon. I just kept that the same just for this discussion. These two electrons are moving over. So now this beta prime carbon had become what? What's the classification of that carbocation? So it's tertiary. So what we did, we went from secondary to tertiary. So secondary to tertiary. This is one path. Let me show you, or let me ask you a question. If you were considering this beta carbon here, and you did the same sort of migration, one of these hydrogens moved over as hydride, how would you classify the resulting carbocation? What would it be? It would be primary. So I'm going to draw that. So that does not occur. So the reason that does not occur again is because you're secondary to begin with, and to go to primary would be going higher in energy on that reaction coordinate, and you're not necessarily going to do that. So if you're at secondary, you can drop down to tertiary because you're forming something more stable. So now look what you've done. See this carbon? It's electron deficient. You see in the product, now we can form that bond to that oxygen from the solvent. So this is where the solvent finally comes in. We have HOCH3. So now this is a Lewis base attacking a Lewis acid, so nucleophile attacking electrophile. So we're left with this intermediate here, which is a protonated ether. So we're going to do a proton transfer. So you can show that with the solvent if you want. And so these PT proton transfer, that's fast. And so that's how you end up with your final product, with the solvent slash nucleophile attacking a different position from where you started with after you ionized. So is everyone clear on carbocation rearrangements and why they happen? So let's we'll do another mechanism, and sort of this will answer what Aiden had asked about neopentyl centers. So here's the reaction. We have this bromide we're treating with a polar protic solvent in heat. We end up with a substitution product. So what is the classification of the halogen? So it's a secondary bromide. But it's also neopentyl. And again, what do we mean by that? Neopentyl is basically this position here where you have a tertiary carbon next door. So if we count 1, 2, 3, 4, 5. So 5 is pentyl, right? So neopentyl basically means you have a position. So this secondary position, it can be primary as well, but the position next to it is tertiary. So see how this has 1, 2, 3. So this is really sterically congested. So you have a secondary substrate. You know that there's a decision point there, whether you determine if it goes SN2 or SN1. The solvent is polar protic, so that's telling you of that sort of flow chart, you now have to go into the SN1 manifold because you're polar protic. You don't have a very good nucleophile. So considering the starting material and the product, what's the weird thing about this product? If you had to verbalize something. So the ethoxy is not where the bromide was. So again, these are the questions that you have to ask yourself as the student when you're learning this material. Like your eye is telling you, okay, there's something strange going on here. Now mechanistically, you have to propose arrow pushing steps that describe that without violating anything you've learned so far. So Blakely and Aiden are cluing into what's happening. So let me put some numbering here. I'm a fan of numbering these things. So if I say, so 1, 2, 3, 4, 5, 6. You can see here that this 2 carbon has two methyl groups. Now in the product, that no longer exists. If I keep the numbering consistent, 1, 2, 3, 4, 5, 6. So Aiden says the methyl group switches places. So that happens through not a hydride shift, but a 1,2 methyl shift, where the 1 and 2 are just telling you the relative locations of that methyl group. So what is the first thing we should do in showing the mechanistic step for this reaction? What's the first arrow we should push? So yeah, we're going to ionize the bromine. That's our slow step. You might see this nomenclature RDS, which is rate determining step. We saw from above we're generating a secondary carbocation. So again, you ask yourself a question. That's the alpha carbon. Here's beta. There's beta prime. Beta is not equal to beta prime. So that clue there, beta prime, is more substituted. Once you sort of categorize that, that gives you a clue in guiding you mechanistically, because rearrangements they must occur from the more substituted beta carbon. So in this case, because beta prime is more substituted and there's methyl groups, the methyl group is going to shift. So now what is the classification of this new carbocation? So it's tertiary. So we're allowed to do that. What if we notice this beta carbon, those two hydrogens? What if one of those hydrides migrated over? What would you end up with? If a hydride migrated over from beta here, what would the classification of that carbocation be? So it would be secondary. So in general, degenerate or the same carbocation rearrangements are not allowed. So you really wouldn't go from secondary to secondary. So we've in this arrow pushing here, this migration, 1,2 methyl shift. We've set ourselves up for success because now this carbon is electron deficient. So what are sort of the last things we have to do to get to the final product? We have the solvent, which is the nucleophile. It's the Lewis base. It's supplying electrons to the electron deficient center. We just need to do a final proton transfer. That usually comes from the solvent. And so that gets us to our desired product. So again, when you're given a situation like this and you're asked to propose a mechanism, the mechanisms are going to follow sort of what we've seen. Substitution, SN2 versus SN1, and those things differ in terms of the solvent, the nucleophile, the stereochemical outcome. So while we're talking about stereochemical outcome, let's do one more example. So this is actually one from your book. So we have the following substrate. So how do we explain what is happening here? First, what is the name of the starting material using the CIP stereochemical designation? So let's also consider the stereochemistry. So we have S2, 3 dimethylpentanol. How many stereogenic carbons are in the starting material? So we have one. So there's a review. We have 1, 2 to the 1 is 2 possible stereoisomers. We're showing the S. Now in the product, how many stereogenic carbons are in the product? So we have 1, so we have 2 possible stereoisomers. Now I know it's subtle, but in the starting material, we're specifically showing this as a wedge and this as a dash. That allowed us to determine this, correct? Here's the stereogenic carbon in the product, but now look. We're not showing any wedges and dashes here. So what can you infer about this product? If you're starting with pure S, what do you end up with here? So it's racemic. So the question is, why is it racemic? So yeah, it's going through an SN1 mechanism. You have a tertiary alcohol. You're starting with a polar protic solvent / nucleophile, an acid. So this is an acid. This has to act as a base. You'll notice when you're starting with an alcohol, that does not happen. The alcohol never ionizes to give you a carbocation and hydroxide. How do we explain that? Remember when we talked about leaving groupability, we were looking at pKa's of 0 to negative. So the conjugate acid of this base is water and the pKa is 16, so that's a terrible leaving group. So whenever we have an alcohol, we have to activate the OH. We do that through protonation. The alcohol is the base. It's being protonated by the HBr, so that's an acid-base reaction. Proton transfer. So now this is a better leaving group because it's going to leave as water. So I'm balancing out the charge now. So this is what happens. This is sp3 hybridized. It has chirality. We determined it to be S. After this ionization happens, it's now sp2 hybridized, and we saw before this is flat. You have the p orbital above and below, so you've lost the stereochemical information. The bromine has equal opportunity to attack from the top or the bottom, and that's how you end up with the racemic mixture here. So what is, and you can just draw that attacking, or I'll put the arrow in. If you put this sample in a polarimeter, what does the specific rotation end up being? So it ends up being 0 because whatever the R rotates, the S rotates it the opposite way, so you end up with 0. So we are about out of time for this chat. Your Module 4 exam is on Friday. You'll have 90 minutes to do it. The same format as the other prior 3 exams. Your homeworks are all due at 11 in the a.m., not p.m., so 11 a.m. they're due. If you have any questions, am I making the question type like the last exam? So to answer Hannah's question, yes. So of the 3 chapters, you will have easy, medium, and difficult questions from each. So I think it was like 8, 8, and 9 or something. So I'll put that breakdown in the Canvas module right in that that link to the exam that'll show you there. If you have any questions, shoot me an email. I'll respond as soon as I can. Yeah, the exam opens Friday and it closes Saturday. Again, you have 90 minutes to do it once you start. Other than that, I'm going to go ahead and sign off. Again, shoot me an email if you have questions.